Yeah, in the view. Yeah. Ah, there. Ah, that's, thank you. Yeah, because it looked strange. Okay. Yeah. Okay. Sorry. I think that doesn't work exactly right, but okay. Let's wait. Let's open it differently. Oh no. Oh, now I lost it. Okay. Where is it? Ah, here. There. Open with either. Yeah, I think that's better. Yeah. So that's why I'm lost because. And then there is usually view. Yeah. See. Ah, yes. Okay. Okay. Now I think now it works. Okay. Sorry for the delay. Okay. So thanks a lot for inviting me to be here again. It's very nice to be back in Natal. And especially it's nice to come back to talk about a project that which first emerged last year when I was here in August, and we discussed about this, and then this has now become, well, almost a finished paper. I think it will be finished very soon. As I was listening to the talks in the last few days, especially a couple of days ago, I realized there were lots of talks about GHD, of course, which has become now a rather big field. And at some point, I had this feeling that I was going to be the only person in the room that was not going to cite my own work. And I felt a bit silly, a bit stupid about it. So I wanted to find a reason to cite my paper somehow, even if it's just to say that it's not about this. And of course, their paper, yeah. I have to cite both. So this is not about hydrodynamics, and it's not about generalized hydrodynamics, but it is about dynamics. So at least I'm trying to get there. So the other day, it's quite funny, the other day I was talking to Eric, and through a careful process of discussion and analysis, we came to the conclusion that I was the founding mother of the GHD field, which is kind of it gave me a confidence boost in the moment. I felt quite important. Then I immediately realized I was the oldest woman in the room as well, which kind of took that all away again. But it's kind of funny because as founding mother, I wasn't very good in a sense. I think motherhood is not for me because as soon as the baby was there, I just left. I left it with the 6 fathers. I mean, they should be able on their own. And they have been. So I was very impressed by that only 3 years later, so many beautiful things have come up. It has become this really big and incredible field. So that put me in a poetic mood, and it reminded me of a quote that I like a lot, and I think it kind of applies a little bit to GHD now. Maybe some of you know it. It's very famous. But essentially, the first part is that whilst this planet has gone cycling on according to the fixed law of gravity, which in my case means while I have continued computing Rayleigh entropies, from so simple a beginning, the continuity equation, essentially, endless forms, most beautiful and most wonderful, have been and are being evolved. Diffusion, superdiffusion, all sorts of things. So what an ending for a book, isn't it? I wish I had written that. Well, I didn't. Okay. So with that, I'm going to come to the point of what my talk is about. So it's not about GHD, but it's about the dynamics, quantum dynamics after a quench. So this is something that, of course, many of you know about. And it's actually quite related to what Robert just talked about and what Gabor just talked about the other day. So this is based on a work that I have done with these 3 nice people, these collaborators, Jacopo, Mate, and István, about entanglement dynamics in the Ising field theory. And I would like to also thank actually the Research Council that has been funding István and I through the past 3 years. Okay, so as I usually do in my talks, I think it often works better to first tell you what the result is and then tell you what the techniques are, because probably many of you are not that interested in the precise techniques. So, and the results are actually simple and easy to understand and easy to explain. So I will start first by telling you what the problem is. It's a very simple problem, and some of you might think, but is there anything new to understand about this problem? Well, there are some things, actually. I hope I convinced you. So this is about the Ising field theory, simplest QFT you can think of, massive. So we have a mass scale, and we are thinking about the kind of basic quench, a global quench where we change the mass. That's all. So we change from this mass m0 to a mass m, find 0, and we look at what happens at that system. Now, what we want to look at, particularly what we have done in our calculation, is to look at the entanglement entropy of a semi-infinite subsystem after a certain time. Okay, so this is entanglement dynamics. And so what we have, kind of geometrically, is a system that is just divided into two parts, and you have to think that A and B are both semi-infinite, so very large. And then we have this famous picture Robert just showed us in the previous talk and explained at length by Calabrese and Cardi, this famous picture, quasi-particle picture. So perhaps it's worth emphasizing, in comparison to what he said, most of the time we think about this quasi-particle picture, we think about it in the way Calabrese and Cardi described it, which was for a finite interval. And if you have a finite interval, then you have two phenomena, as Robert said. You have linear growth in time, but you also have saturation after a time that's proportional to the length of the interval. But if you're looking at an infinite interval, then there's never saturation. You just have growth in time forever and ever. So this is what we expect, and this is what we are going to find. So, and this is important to notice because actually we're going to do some analytic computation and we're going to compare it to numerics. And the numerics actually, they will be done on a finite interval. So that comparison would in some sense fail, and that's precisely because of this difference here. So this problem is very well understood in the Ising chain, which is the lattice version of the model that I'm looking at. It was very well described, understood by Fagotti and Calabrese, so they precisely computed the coefficient of this linear growth in time, the coefficient of saturation. These are functions that are known explicitly. And in fact, although I'm not going to show it, from our QFT calculation, we have been able to take, well, from their calculation, we have been able to take scaling limit and to see that that agrees with what you get from QFT, from what I'm going to tell you. So, of course, both things should be related. For the Ising chain, there is also a very good understanding of other operators, in particular, the dynamics of magnetization has been studied very extensively. And this is actually, relevant in here because what we're going to find is that the dynamic of entanglement and the dynamic of this other field are actually very closely related. They are not really completely different from each other. And as I already mentioned, I think many of the features, the ideas I will describe, for example, the appearance of oscillations have already been mentioned in other talks, but it's in a much simpler model and with very different techniques. So we cannot see confinement because we have only one particle type. So there's still the line going effect, if you wish, but we're going to have oscillations around that. Okay. So this is the problem. Okay. Now let me tell you what we are actually computing precisely. So we're going to compute something that actually Germán Sierra and collaborators have called excess entanglement, so the difference of two entropies. In this context, actually, the word excess is a little bit misleading because this difference in this particular context is not necessarily a positive quantity. So if you see some graphs where functions become negative, it doesn't mean it's wrong. It just means that actually the entanglement after the quench is not always necessarily bigger than before the quench, which is what we are computing here. Because the ground state of this Ising chain before the quench is already highly entangled. It has an entanglement that is non-trivial. So this is the difference. I mean, what I'm defining here is a Renyi entropy. It's a function of a parameter n. And it's the difference between the entanglement at time t after the quench and the entanglement at time 0, just before we did this quench. Okay, so at t0, this is a function that should be 0. That's the idea. And what is this function? So let me give, I think probably the first time this definition is given in this conference, which is funny. I mean, before GHD existed, there used to be this formula like 55 times before we came to my talk. But people are not doing so much entanglement nowadays. So let me give you the definition. So this is the Renyi entropy as a function of n. And this is a function of another thing, which is a trace of a reduced density matrix raised to this power n. Okay? The limit when n goes to 1 of this function, which I kind of a bit liberally call S1, this is what we call the Phonemic entropy. Okay? So this can be done. And this reduced density matrix here, well, in this case, at least formally, it is going to be this function here. So it is a matrix that's constructed from the ground state before the quench, which is that 0 in there. And upon this ground state, we are acting in the Heisenberg picture with the time evolution operator. But this time evolution is now performed by a Hamiltonian, the Ising Hamiltonian, depending on a different mass. Okay? So the mass for this pre-quench state was m0, but the mass on this Hamiltonian is m. Okay? That's the quench that we are doing. Okay. So this is what we are computing. And if you're doing a computation in the lattice for the Ising chain, I mean, which is very simple, you can access, essentially you can compute this trace of rho to the n. Explicitly, you can do that by using a method which is called Toeplitz determinants, which is what we have done in the numeric part of our work. So you can essentially compute explicitly the eigenvalues of these metrics, raise them to the power n, add them up, and compute your entropy. Now, my specialty is more from quantum field theory, so what we wanted to do is to compute the same thing using quantum field theory techniques directly in the Ising model. And the one technique I'm very familiar with from working, I have worked on that for a very long time, but for equilibrium states, is something which is called this branch point twist field technique. So this project is not just about some new results, which there are, but it's also a little bit of a proof of concept that this twist field actually is also useful out of equilibrium, okay? The things you can compute, and they do make sense. So let me tell you very little about it. If you have ever heard talks by me, I'm sure you probably have heard about this. But the idea is very simple. The idea is that in quantum field theory, both in one dimension at least so far, both critical points and beyond them with a gap, it is possible there is a one-to-one correspondence between measures of entanglement and multi-point functions of these branch point twist fields. And in fact, the multi-points, so the number of points of this multi-point function, is exactly the number of boundary points of the subsystem that you are considering. So in this particularly simple case I'm looking at, we only have a boundary point, so this is going to be a one-point function of this branch point twist field. So what we need to compute, if we want to use twist fields, is a one-point function. And so these Renyi entropies that are introduced in here, in this twist field language, they become these things. So you see that the trace of rho to the n essentially becomes this one-point function of this new field t. Okay, so this t is the twist field. At position 0, we're going to put the kind of boundary in regions between regions A and B at 0, and at time t after the quench. And this 0n in here, this is still the pre-quench ground state. But now there is an n in there just to indicate that this twist field, by construction, is a field that only makes sense in the replica theory. So in a theory which is, in effect, n copies of the Ising field theory. Okay, so this is how this technique works. First, you do n copies of the theory. In those n copies, you have a cyclic permutation symmetry, and associated to that symmetry, you have this field. Okay? So you have to compute that one-point function, divided by 1 minus n. Everything else is the rest. In quantum field theory, it's common to write also some parameter in here, some epsilon. And this epsilon is thought of as a UV cutoff. So essentially, it just means that this entropy is not purely defined by the one-point function, which is kind of universal in QFT, but there's going to be some non-universal corrections to that. And one way to think of this, if you are more familiar with the lattice, is that this epsilon essentially is proportional to the lattice spacing when you go to the lattice. So it scales with some dimension, which is actually the conformal dimension of this twist field, which is known. It's a function of n and the central charge. And what is nice is that if you're computing differences, such as here, the dependence upon this cutoff, upon this epsilon, eventually should go away. So we should get something that is universal, both in the lattice and in the QFT, hopefully, if we want to compare. So this is what we are computing, okay? So that is the problem. How do we compute that? Okay. So what's next? Well, what is the solution procedure? So I'm going to tell you what methods we have used. Essentially, they are methods that were already known, but what we have done is to adapt them to this field, to these replica theories, okay? And that required a little bit of work. It's not too complicated, but there is some steps. So essentially, what I've told you is that entanglement dynamics is in one-to-one correspondence with this branch point twist field correlator. So we have to generalize some techniques or find some techniques to compute that. So when we started our work, there were two techniques we were aware of to compute dynamics of one-point functions after a quench. In particular, in Ising, there is quite a bit of work about that in the QFT. And the two techniques that we knew and that we have used and generalized are the following. So I'm going to tell you what they are in words, and I'm going to tell you what I think are the pluses and minuses of each of them. So they are quite different, in fact. They're both perturbative, but different. But yeah, so let me tell you. So the first technique that we have used is called perturbation theory about the pre-quench state. And this is a technique that was proposed by Aldo Delfino a few years ago. And this is perturbative in a certain sense. It has so I'll tell you in a minute, but one of the big pluses of this technique, in a way, is that it is applicable to any global quench. So if you're having, in an integrable model at least, so if you have an integrable model depending on some continuous parameter and you are quenching on that parameter, then in principle you should be able to apply this technique, no matter what the parameter is. Now there is some minus to this technique, and one minus is that it is perturbative in the size of the quench. So in our case, the quench is in the mass, and so this technique really is only applicable if this quantity here is rather small. Okay, so we are doing a very tiny quench. Okay, so if this is what you want to do, that's fine, but if you want to look at bigger quenches, it's not so useful. Something that is also limiting in this technique is that actually, in the work of Delfino and some other extensions, it has only ever been used really at first order in perturbation theory, and actually developing it to higher order seems to be rather non-trivial. I mean, we did try a little bit at the beginning, but there are singularities to deal with, and it's not so easy to generalize. And so, in conclusion, this technique is good, but it will only capture first order features for small quenches. And that is okay, but in fact, for us, is not entirely sufficient. It is interesting because it captures something interesting, but it's not so satisfying because actually, in this particular case, it turns out that, for example, the linear growth of entanglement, which is kind of the main feature you would expect, is actually a second order effect on the size of the quench. So if you use this technique, you don't see linear growth at all from this computation. So there is another way of doing things, which is also perturbative, but in a rather different way. And this is a technique that Schuricht and Esler used in 2012 to study the one-point function of the spin field in the Ising field theory. And this is a technique that is perturbative in time. So it's what it gives you is a large time expansion of the correlation function, whichever one you are computing. So the one-point function is based upon a form factor expansion, and is based upon form factors of the post-quench theory. So in that sense, they're also different. So if you look here, in Delfino's technique, we expand around this pre-quench state. We do perturbation around that. In this other technique, kind of the fundamental objects are in the post-quench theory. Okay, it doesn't make a huge difference, but conceptually it is different. And what are the advantages and disadvantages here? Well, there is one disadvantage, perhaps, which is that to use this technique, the pre-quench state has to have a very particular form in terms of post-quench states, and this form is sometimes called a squeezed coherent state. So it has a very particular expression, and I'm going to show you where it is a little bit later. Okay? So it means that it's not entirely general as the previous one was for any global quench. It's just some quenches. The nice thing is that there is no restriction on the size of the quench a priori, so you can have now large quenches if you want. The form factor expansion that emerges from this can a priori be developed at any order, so that's also good. There is something which is, I think, good and bad in a sense. Kappa regularization technique is used, so essentially when you do this form factor expansion, there are singularities that occur. You have to deal with, you have to regularize in some way. And the way Schuricht and Esler did it was by using something called Kappa regularization, which was developed by Robert and Fabian a little earlier, in other words. And this technique is nice, I find, because it's simple to use. But it has, I think, a drawback, which is that it's not perhaps entirely rigorous. It's not as rigorous as doing full finite volume regularization, which is, I think I would like to understand better in that way. But it works. It works nicely. It works for the spin field. It works for the twist field as well. And perhaps something that is something also good is that this is going to capture higher order features for small quenches. So you can go higher in perturbation theory, which is nice. It's an advantage with respect to that. Okay, so these are the two methods. Okay, so let me show you the results. I told you I was going to start by showing you the formulae, so I don't lose you all with all the technicalities. Then I'll come back to the techniques if we have time. So the main result is the one-point function, right? This is what we wanted. This is the building block of everything. And the formula that we get for that, perturbatively in time, is a formula that looks like this. Now, if any of you here is familiar with the work of Schuricht and Esler, you will find this formula very similar to what they found. And indeed, it is very similar. It is computed in pretty much the same way, and it exhibits exactly the same features in some sense. So what do you see? You see that this one-point function of twist field in replica theory admits a 1 over t expansion, if you wish. And this expansion looks like that. The various terms in there. There is a constant term in here, which is this term here actually is the backing expectation value of twist field in the ground state of the post-quench theory, so the ground state of Ising with mass m, if you wish. That's something that is known. We have, what else? We have this parameter mu is actually 1 minus m over m0. So this is kind of a function of the masses, a function of how big the quench is. If the quench is small, that's going to be a small parameter, essentially, proportional delta m. So you see here that there are terms of order mu, so they will be of first order in this. and you have terms of order mu squared. For example, this 1 over t. So this is a lower order effect in terms of size of quench. You see that there is this exponential decay of the one-point function, which is a common feature of one-point functions after quench. So this is also happening for the twist field. And this gamma, this is a function that is known explicitly. I'll show you later. But for now, I just tell you that it has an expansion also on this mu, and it's also of order 2. Okay? So this exponential decay is also an effect that you are not going to see in first-order perturbation theory. You will only see it with another technique. Okay, and this gamma, in fact, is exactly the same gamma, the same decay rate that Schurich and Esler found for the magnetization, for the spin field. It's exactly the same function, if you are familiar with that, what that was in there. But now it's dressed by this n, with this copy number, and there's this 2, this factor 2 in there as well. But otherwise, it's exactly the same decay rate. For small quenches, the leading feature, if you look at this formula, what you see is that for mu rather smaller than 1, the main feature that you're going to see actually are oscillations. So this is similar to what Robert was telling us, to what Gabor was telling us. There are oscillations. These oscillations, they are not going to kill the licon, so there's going to still be linear growth in time. But for the one-point function, they will, for small quench, this is the only feature we're going to see. Oscillations of frequency 2m, and amplitude that decays with 1 over t to the power 3 half. Okay? And these oscillations, as far as I know, I mean, for the gap regime that we're looking at, had not been found previously in the literature. In fact, in the literature, which I don't quite understand why, but there is a statement, explicit statement in the work of Fagotti and Calabrese that says, for h bigger than 1, oscillations do not occur, which is exactly the regime we are in. But in fact, our numerics and our computations seem to say very strongly that they do occur. They are absolutely there. And actually, they are the most robust feature that we see. So we have no doubt that they're there. Okay, so something that is interesting about this, perhaps not so surprising, but I find it quite deep, in fact, is that the exponential decay of the one-point function, which is totally expected after quench, when you compute entropies, which are logarithms essentially of that, this is what becomes the linear growth in time. Okay, so in a sense, the behavior of entanglement is not entirely distinct from the behavior of everything else. It's just a consequence of the standard behavior of one-point function, many-point functions, the logarithm of that. So if you have, so this becomes growth because you have to divide by 1 minus n after taking the log, which is generally negative. So that's going to give you a linear growth that I'm going to show you in a moment. So exponential decay is linear growth, okay? So from our definitions then, we find that this excess entropy, so this quantity which was the entropy after quench minus the entropy before the quench, has an expansion that's going to look something like this. Okay, so we're going to have a constant. Okay, this constant is essentially the result of putting together the vacuum expectation values of the twist field before and after quench. So it's a function of the ratio of the masses again. And in fact, okay, this is something that we still have to complete a little bit. That's why this paper is not finished yet. But there's a suggestion in the work of Schurich and Esler that this constant actually acquires corrections of higher order if you keep doing your form factor calculation. So that means that this is perhaps not the exact constant in there, but it's pretty close if the quench is small. And then what you see the linear growth I was telling you about. So, okay, so you have this increase with this gamma. That was the exponential decay rate. Now it becomes linear growth. Then you have a 1 over t term, and then you have oscillations with 1 over t to the 3 half, and then you have more subleading terms, oscillating terms, etc. So lots of things. But this is the main things that you are going to see when you do numerics, for example. So all of these terms, again, are very similar to what was seen for the magnetization. And this formula is actually very well reproduced numerically, up to a little offset, so kind of adding a constant to everything, perhaps because of what I told you about this constant. And something that you might have noticed if you're thinking a bit more about this formula is that if you take the limit n to 1 of that formula, which should be the Phonemic entropy, you'll see that some of the terms are actually ill-defined in that limit. So actually, the oscillatory term, it's OK. You can take the limit n to 1, and it works. You get something finite, and you get something that agrees with numerics. But for the other terms, you are dividing by n minus 1. So there's obviously a problem. Now, it's not that this is wrong. I mean, I'm quite confident this is right. But this has really to do with the technique by which this is computed. So when you do these branch point twist fields, you assume as a matter of principle that n has to be an integer bigger than 1. Okay? So taking the limit n to 1 is really non-trivial. And we have done a lot of work in the past just to work out what the proper analytic continuation is that allows you to do that. So we didn't do that work in here, which means that these formulae are not true if you want to generalize to completely generic n, that is real non-integer, okay? So we cannot take the limit directly in here. That is fine, but this is going to give us at least the Renyi entropies correctly. Okay. So what else? Well, you can also, if you want to look at very small quench, you could take that formula and modify it further and expand it when the difference of the masses is very tiny. And if you write it in that way, this is, again, the formula you get. So you have your linear term in T and your 1 over T, both of which are of second order in the size of the quench, so undetectable by this perturbation theory of Delfino. And then you have the linear term, which is essentially oscillations and part of that constant I was writing before. Okay? So this I already said. For small quenches, the two techniques I talked about, they completely agree with each other. So if you do this calculation with Schurichen-Essler technique, Delfino's technique, you consider small quench, and both give you this oscillatory part exactly in the same way. So this is a good sign. The linear term in T is also in perfect agreement with the scaling limit of the Ising chain result up to a factor 2, and this factor 2 gave me quite a few sleepless nights because at some point it was missing, but then we found it. And this factor 2 is very important because it's a reflection that clustering is also a property of the twist field. So the idea that if you have a 2-point function for large separations, that should become a 1-point function square. So when we compare to numerics, really what we are comparing to is this with large L, but what I am computing is this without the square. So when you take the logarithm, it's a factor 2 that has to be there. And it is, so everything works nicely. Okay, so let me show you now some numerical results, just to convince you that this really works. And then I'll go to the techniques in the time that's left. So this is a picture of the Phonemic entropy for a system. So the dots are numerics, okay? So this is Phonemic entropy for system size L, different system sizes. And then on top of it, there's a continuous curve, which is essentially the analytic prediction for the oscillatory part of this formula. So essentially, this is just trying to show you that the oscillations that we see numerically are in precise agreement with the oscillations that are predicted. Yeah? From a Toeplitz determinant calculation. Lattice, yeah. Spin chain, yeah. I mean, Ising chain, yes. Okay? So Ising chain with magnetic field bigger than 1. Okay? And so, actually, this is written here, sorry. So this is for this model, and we're taking h bigger than 1, which is the gap regime of the theory. And as you know, probably in the scaling limit, the mass that we see in QFT is proportional to h minus 1. Okay, so this is how the scaling limit then is done carefully. So, so I guess the main message from this is that the oscillations are very well predicted. Really, they are there, and they actually are long-standing. So they persist in time, even after you have reached the plateau. Okay. So what are we seeing here? Well, this is actually the quench. So the masses are rather small, but the quench itself is not that small. Like in terms of this, about 10% change in the value of the mass. The data that were shown here are for different subsystem sizes. Okay, so from 500 up to 900 in steps of 100. So the bigger the subsystem size, the higher this curve is. And what we are seeing here is a comparison, well, with the analytic formula plus offset, a little offset. So what do we see? Well, we see that for short times, all of these numerical data are on top of each other. That's why we only see some dots in there. And actually, this part in here, this is the linear growth in time, okay, of all these entanglements. They all grow in time linearly, okay, in the numerics. But then they saturate, as we expect from Calabrese and Cardy's interpretation. They saturate to a value that depends on the size of the subsystem. So it's a different value for each L, but it's proportional to L, okay? So that is expected. And the oscillations, however, on top of the saturation value, these oscillations still persist. So they are clearly visible in there after saturation. And they're well reproduced up to the famous factor 2, which is also there, okay, as it should be. So this is one example. Another example, perhaps that's even nicer, is this one. These are Renyi entropies, I think, yeah, for N2, 3, and 4. And what you see here is a comparison of the full analytic formula that I show you up to a little shift to be exactly on top of the numerical data, compared to numerical data. So the data here are for much bigger subsystem size, 2 to the 11, so 2048 sites about. And so the saturation of the numerical data happens quite a lot later. But you see here the numerics, you see the linear growth and the oscillations, and then eventually saturation. If you compare to our formulae, you don't see saturation because our formula, they don't saturate. They are for infinite system. Yes? So partially. I mean, we're still thinking a little bit about it, but I think at least there are several effects that are probably together in there. One effect might be, I mean, and maybe Mate can say more about this because he's done the numerics, but one effect perhaps is maybe not being completely fully in the scaling limit, so you can always get a little bit closer. It's a constant. It's just an overall constant that you add, okay? So it's a little effect. I think another effect is what I said earlier, that the constant that you predict from QFT actually has corrections. There are some corrections. So when the quench is a little bit biggish, like this one, 10%, those corrections might have a tiny effect, okay? So maybe we're not predicting the constant exactly right, okay? But there's no fitting parameter. That's the only thing that we're doing, just shifting the curves a little, okay? So that's the size of subsystem. And, okay, as expected, we have agreement with the analytic results, okay? So I think this is it in terms of describing what the results are, what the numerics are. I don't know if you have questions about it. I mean, this is the result. What I want to do in the remaining, well, 20 minutes, 25 minutes, if I can, is to tell you a little bit more precisely how these techniques are used, what they are, and then conclude, okay? So I'll start with the first one. So the perturbation theory, I call Alla Delfino, just to separate from Alla, Zurich, and Esler, let's say. It's a very simple idea. So it's the idea that if you do a small quench on some parameter of the theory, you can interpret that as essentially going from some action functional, depending on this parameter, lambda 0, say, to a new action functional, which is the original one, plus a perturbation, okay, a small perturbation. And that perturbation is characterized by some local field of your pre-quench theory and, well, by some small parameter lambda, okay? So if this lambda is very tiny, in absolute values, that would be our delta M from before. Perturbation theory is applicable, and essentially what you can say is that the post-quench state, it will be a time ordering of something that looks like this, so the exponential of this bit of perturbation of the action, if you wish, acting on the pre-quench state. Okay? So this is the perturbation theory about this pre-quench state. Now there are a few little, I mean, there are a couple of steps in here, but not too many. Essentially, if you expand this exponential appropriately, you end up with a formula with an expansion for this post-quench state, which is the pre-quench plus corrections, which at first order go with this small parameter. And those corrections actually in 1D integrable models, or in 1D models, in fact, they're going to look like this. So you're going to have many of them still, even just for this first order term. It's an infinite sum. You have a delta here of the momenta, pre-quench momenta, so M0 cos sinh theta, and the energies, M0 cos theta. You have here some matrix element of this local field phi, and you have here a state. Okay, so let me actually show you the formula. So this is a form factor we heard about yesterday, form factors. A form factor between this pre-quench vacuum state and a generic state of the pre-quench theory with K particles. Okay? So you have this description of the state at first order in perturbation theory. And now if you want to compute a one-point function of any field, for example, that field there, phi, the only thing you have to do is to sandwich the field between these two states, expand the state, and develop that formula. Okay? It's not very difficult. I just showed you the final result. In the work of Delfino, what he does generally is to not compute just this one-point function, but compute kind of like us, the excess, so the difference between one-point functions before and after the quench. And the formula he gives for this is that. So it's going to depend on form factors of the perturbing field and form factors of the field you're interested in. And this one in here is kind of put by hand just to make sure that at T0 that is really 0. Okay, so it's kind of the constant put in there, our constant. Okay, so so that is the result. And so in summary, given an integral model and any small local quench, you can use first order perturbation theory. The only thing you need is you need to know the form factors of your fields. Okay, so if the theory is very complicated, maybe you don't. Now, in the Ising field theory for the mass quench, this is particularly simple because the mass quench is in the mass quench, the perturbing field is the energy field in Ising, and the energy field actually only has one non-vanishing form factor, which is for two particles. So this whole sum becomes just one term, okay? At first order in perturbation theory, so it becomes very simple, okay? So this is that. Now, if you want to do this for the twist field, it's actually really very, very simple. So there's not much to explain. The same formula holds pretty much, putting T instead of phi, replacing lambda by delta of the mass. And you have an N in here that is telling you that you now have N copies of the theory, so this N appears naturally. And the form factors here, those of the twist field, and because this twist field lives in this N-copy theory, you have many form factors you could put, but the one that matters really is the one where all particles are on the same copy. So let's say copy 1. It's the only one that is going to feature in there. Okay? So you have N times that, sum over copies. Okay, so this is the energy field, as I told you, and all of this I have said already. Okay? So this constant is there also to guarantee that. So if you use this formula, this gives you essentially the oscillatory terms that I showed you earlier. I think I have that here. So just by doing that computation, it's not too complicated, you get this formula in here, up here. So that was the oscillatory part, first order perturbation theory. And if you do the limit n to 1, you also get the oscillatory part for the Phonemic entropies. Okay? And this matches very well with the numerical data as long as the quench is small. So as long as m and m0 are quite close to each other. Okay? Okay, so here's another picture of a similar thing, just showing again the oscillations. And in fact, here there's emphasis on something that is not that important, but just that this 1 over t term that also appears in the expansion from Schurich and Essler, it provides a small improvement on this matching with numerical data. So it looks like it's really there. Okay? But this is, okay, a technical detail, not so important. So, okay, so this is that. Let's now talk about Schurich and Essler a little bit. So I told you that their method was based on using the so-called squeezed coherent states. So the idea of that is that the pre-quench ground state can be expressed in terms of states of the post-quench theory. And the kind of expression that one has is something like this, which I think many of you would be familiar with because this is already relatively old work. So this was computed, I think, in the works of Fioretto, Musardo, and Sotidiades, Fioretto, and Musardo, this K-metrics in particular that actually does the trick of implementing this mass quench. So essentially you have that your pre-quench state, omega, can be expressed in terms of states of the post-quench theory in this way, by acting with this complicated operator. And if you were doing, I mean, if you were around before people pronounced the word quench a while ago, then you would have thought of this state as a boundary state in integral quantum field theory, which is how Goshel and Samorodikov thought about it many years ago. Okay. Now, I call this omega instead of 0, just to indicate that this state is not necessarily normalized to 1, okay? And that is important because what one wants to compute then is actually not just the 1-point function, but this sort of ratio. So we have to take care of the normalization of the state, okay? And that makes the calculation a little bit more complicated, but not too much. So if we want to compute the expectation values, now this is our state, okay? And the generalization to branch point with fields is, again, actually super easy. If you look at this formula here, we have these creation operators for free fermions, essentially, because this is the Ising model. And if you want to do twist fields, the only thing you have to do, actually, is to put a sum in here and to now say that instead of having just one kind of creation operator, you have n now for your n copies. Okay? It's like having n particles of the same mass. So you have this sum. Everything is a tiny bit more complicated, depends on n, so I now put that n in there. But what we are computing is essentially very similar. Okay? So the result is an expansion. The result of trying to compute this is a complicated expansion in matrix elements of this branch point twist field. Okay? When you expand this exponential, you see what's going to happen. And this is also, by construction, an expansion in powers of k. So you can also see this as a perturbative expansion on this function k, which is itself proportional to delta m. Okay? So it's a kind of perturbation theory, but on a different parameter. So the form of these form factors of this twist field is, of course, a lot more complicated than for the spin field that Schurich and Essler studied. But as Jacopo was saying yesterday, and it's a bit the same idea, the nidicity structure is the same. So you know that in the M form factors are very much characterized by the position of the poles, kinematic poles, things like this. And this actually is what determines to a large extent the results of computations. So in that sense, the computation is very similar. And many things just go through in the same way they did them, but with few changes. Okay? So I'm going to just show you a little bit, but with not much detail. Okay, I'm almost done. So the idea is that you take this pre-quench state, you expand it, and you can expand it at the, well, first leading order, more or less. This is already complicated enough if you do that. And if you then plug it into this ratio here, well, you're going to get various contributions. So at first order, you will get the contribution from just replacing omega by the ground state. So that's very simple. that's what gives me this backing expectation value of twist field at equilibrium. Okay, a constant. This is my constant from before. If I go to the next order, which is when I put this bit of the state on the right-hand side or the left-hand side of the operator, only on one side, then I get two contributions. You see that there is this k matrix and its conjugate, k function and its conjugate. This little f is the form factor of twist field, two-particle form factor, which is this function there. It doesn't matter where it comes from, but it was computed a while ago. And what matters is that if you do a stationary phase analysis of this formula here, what you get is the famous oscillatory contribution to entanglement. So it comes from that calculation. It looks pretty much the same as the formula that you get from the perturbation theory of Delfino, but now you see that instead of having M0, you have M's everywhere. So this is not perturbative in the size of the quench, in the mass. Okay, it's a bit more general. Okay, however, if this is small, this red bit, then again you recover the previous result. Okay, so this is telling us, okay, there are oscillations. There are oscillations of the entanglement. Okay, and then finally, we have to look at the next contribution, and the next contribution is the one that is really complicated to analyze. Okay, there is a lot of pages in the work of Schurich and Esler doing that calculation that I studied conscientiously and tried to kind of adapt for our field, and I think I succeeded, but it's not that simple. What you see here is, well, that is actually the main contribution one has to compute. There are many terms that arise from calculating this. I'm not going to show you all of them. But you see here this kappa. This is this kappa regularization I was talking about before. So this matrix element naturally will have some singularities. And one way to cure them is to shift the rapidities a tiny bit by kappa. And in this kappa regularization method, what you tend to do is you do the calculation. At the end of the day, you expand around kappa 0, and you take the leading term, which is hopefully kappa independent. And that's what happens, okay, at least for the terms that matter here. So out of all the things that come out of this calculation, there is in particular a 4-particle form factor that arises of this twist field. 4 particles in copy 1 and copy j. Then you have to sum over copies. It doesn't matter where all these variables here are. They are rapidities shifted by plus or minus I pi, etc. But what is interesting to point out, perhaps, is that because this is still a free theory, although in n copies, the structure of these form factors is the structure of a Pfaffian. So you know that in fermionic theories, you often have form factors that are square root of determinants of a Pfaffian matrix. This is also true for the twist field. And that means that the 4-particle form factor is just a sum of products of 2-particle form factors. So you have these 3 contributions there. And that's actually also true for the spin field, but with a different 2-particle form factor. So you have a nice structure that you can use. And essentially what you can do is, well, you have to put that inside that integral. You have poles. You have to do some contour shifting, try to understand what the contributions of these poles are. But eventually, at the end of the day, you expand about kappa 0, and you find that the only non-vanishing contributions that you end up getting are 2. One of them is this, and this is the leading non-trivial contribution to this exponential. So you don't get all the exponential. That would be nice. You just get the first term, the linear term in t. Okay, and then you get some other function, and this function can be analyzed with some stationary phase analysis, and that eventually produces this 1 over t term that we saw earlier, okay? And this analysis turns out to be actually rather complicated, okay? That's one thing we're still trying to understand better. So that gives you the first bit of the exponential. So, I mean, it's a big step to say, okay, this is now an exponential. We just got the first bit, so assume the rest is there. So actually, it can be proven that all the other terms are there. Schurich and Esler also did it. There is a simple argument which is based on this Pfaffian structure of this form factor. But essentially, you can show that by considering higher order form factors in this expansion, by picking up the relevant ones, let's say, you can generate term by term the whole expansion of that exponential. Okay? That's essentially the idea. And not only that, you can also show that this full expansion of the exponential is a prefactor for every other term I told you about. Okay, so not just itself on its own, but it multiplies the oscillatory part, it multiplies the 1 over t part. So actually making that argument is not entirely trivial, but it can be done. Okay? Okay, so this is all I wanted to say technically, so I'm not going to bore you with more details. It's a long calculation, but it can be done. So let me just conclude. So the main conclusion for me is something that I find actually very beautiful and very profound in some way, is that when we talk about quenches, very often we talk about operators, and then we talk about dynamics of entanglement. And we talk about these things as kind of rather distinct phenomena. But if you think of entanglement in terms of fields, then they are not distinct at all in a way. You just have that the behavior of entanglement is just the consequence of the behavior of a local field, another local field, which has pretty much the same features as other fields people have studied. Okay, so it's a kind of unifying point of view in that sense. So by relating entanglement to branch point-twist fields, we find that entanglement is just, dynamics of entanglement is the dynamics of correlators of a local field. The clustering of correlators then becomes the same as saying that the entanglement entropy is proportional to the number of boundary points of your subsystem, okay, which is also expected, but perhaps it's not entirely trivial out of equilibrium. It turns out it's still true. The dynamics of these correlators is not unlike that of other fields, at least for Ising. The technique predicts the expected features of entanglement, namely, for an infinite gap system, entanglement grows linearly in time for all times, okay? So that's something that is expected. But then, there are also, on top of that linear growth that goes on undeterred, there are oscillations. These oscillations are suppressed for large times, but they are very well, I mean, they're very extremely robust, and it's very easy to see them numerically and analytically. They absolutely are there. In the form factor picture, one can think of these oscillations as a result of quasi-particle pairs meeting and annihilating, interacting with each other. But it's not like confinement, where really that is so strong that it kind of destroys the light cone. In this case, because we only have a particle type, that doesn't happen. The light cone is still there, but we have all these oscillations around it. Although our calculation is specific to Ising, which you would say, okay, it's very special theory, very simple theory, the way in which these oscillations arise makes me think that they should be an extremely general feature of entanglement, because from a form factor perspective, they're just a two-particle form factor effect. Okay, and if you have a two-particle form factor, I think you will have these oscillations, whatever you do. Okay, so it would be, okay, that brings me to the last slide, which is that it would be nice to extend this to interacting theories, more general quenches, possibly away from integrabilities, a little bit along some of the lines Gabor and Robert talked about, so going kind of perturbing with the magnetic field, so going into the E8 territory. For example, still integrable, but more interesting. Using perturbation theory, perhaps. It would be nice to have a rigorous finite volume treatment of all of this. I said, I like this Kappa regularization, but I find it for the spin field and for the twist field. I still don't know why it works, to be honest, in the sense that these are branch point twist fields, so they, in particular, they have a branch cut that extends indefinitely in space. So how you make sense of this branch cut in the context of a finite volume understanding is actually non-trivial. And I mean, it is nice that it works, but I would like to understand better why. It would be nice to also maybe approach the direct computation of the two-point function, so perhaps even predict the saturation from QFT. And maybe, I said I wouldn't mention GHD, but then it occurred to me that in the talk of Benjamin, I think he pretty much said that GHD is now so advanced that one can compute any correlator of any field, pretty much. So perhaps one could treat more general quenches, inhomogeneous quenches, also using GHD techniques by kind of taking the twist field and generalizing GHD for that. And with that, I'd like to say that I hope you enjoyed the talk and you learned something from it. And if you found any fault with it, it's probably because over the past year I've been very distracted with many other things. And you probably can guess what it was.